Hello, and welcome to my YouTube channel called Statistics from A to Z, Confusing Concepts Clarified. These videos are based on content from my book of the same name, which is published by Wiley. For more information on the book and these videos, please visit statisticsfromatoz.com. This video is the fourth in a playlist on probability distributions. The playlist is planned to include a three-part series on distributions as a whole, plus individual videos on 9 different types of distributions, as well as several on the properties of distributions. See statisticsfromatoz.com/videos for the latest status of this work. You may find it helpful to view the first 3 videos before viewing this one, but that is not required. As usual in the book and in these videos, we'll go quickly through a list of keys to understanding, or KTUs, to give you the overall picture on one page. And then we'll go into detailed explanations of each of the keys. For this video, there are 5 keys to understanding. The first KTU is the Poisson distribution is a distribution for discrete data. It consists of the probabilities of counts of occurrences. The second KTU says, given an average number of occurrences, the Poisson distribution is useful in predicting the probability of X, or more than X, or fewer than X, occurrences in a given amount of time, or distance, or space. Key to understanding number 3 says, there are different Poisson distributions for different values of the mean, mu. The fourth key says that the variance, which is sigma squared, of a Poisson distribution is equal to the mean, mu, and the expected value, lambda. The fifth and final KTU says the binomial distribution converges to the Poisson distribution as its number of trials, n, approaches infinity. And here on one page are all 5 keys to understanding the concept of Poisson distribution. You may wish to pause the video at this point to read them all together. Key to understanding number 1 begins by telling us that a Poisson distribution is used with discrete data. Discrete data was described in the video Probability Distributions Part 2, how they are used. Briefly, discrete data is usually count data consisting of non-negative integers such as 0, 1, 2, etc. The horizontal axis of the graph of a Poisson distribution shows the counts. The probability of each count is shown by the height of the bar above it. Here we show 2 different Poisson distributions. KTU number 3 will explain how the different shapes are determined. KTU number 1 goes on to say the Poisson distribution consists of the probabilities of counts of occurrences. If we want to count occurrences, we use the Poisson distribution. If we want to count units, we use the binomial distribution. But what's the difference between occurrences and units? Let's say we manufacture shirts. If we inspect a completed shirt for defects, the shirt is the unit. If the shirt has 1 or 2 or more defects, we count 1 defective unit, the shirt. This is 1 shirt we cannot deliver to a customer. And we use the binomial distribution in a statistical analysis of the number of defective units. If a shirt has 3 defects, it still counts as 1 defective unit because the unit is the shirt. But if we're analyzing our manufacturing process for the number of defects, we will count the 3 defects as 3 occurrences, and we will use the Poisson distribution. Why do we need to use 2 different distributions for the 2 different types of analyses? Well, the binomial distribution is designed for use with counts in which each trial has only 2 choices, heads or tails, yes or no, defective or not defective. With the Poisson distribution, the count can be any non-negative integer, 0, 1, or 2, etc. Key to understanding number 2. Given an average number of occurrences, the Poisson distribution is useful in predicting the probability of X occurrences in a given amount of time or distance or space. Here's an example with time. Let's say we are operating a small call center, and we have the capacity to handle up to 5 incoming calls in 10 minutes. We have been averaging 3 incoming calls every 10 minutes, so we will use a Poisson distribution with a mean of 3. Now, what is the probability that our capacity will be exceeded in any given 10-minute period? The discrete variable x is the count of calls received in a 10-minute period. The Poisson distribution tells us that the probability of x equals 0 in 10 minutes, and it also tells us the probabilities for x equals 1, x equals 2, and so on. For this example, we want to know the probabilities of x being greater than our capacity of 5. Our approach is to use the Poisson distribution to get the probabilities of x equals 0, 1, 2, 3, 4, and 5. Then we total these probabilities to get the probability of x being less than or equal to 5. This total probability is 0.916 in our example. We subtract this from 1, or 100%, to get the probability of x being greater than 5. So the probability of exceeding our limit of 5 calls in any 10-minute period is 1 minus 0.916, which equals 0.084, or about 8%. This information will be used in determining our staffing level. KTU number 3 says there are different Poisson distributions for different values of the mean mu. We need only one parameter, the mean, to define a unique Poisson distribution, and different values of the mean give us different distributions. Notice in the diagrams that as the mean grows larger, the distribution moves to the right because the mean moves to the right. The individual probabilities get smaller, the bars are shorter. The distribution becomes more symmetrical, and the distribution spreads out. The variance grows larger. Key to understanding number 4 says that the variance of a Poisson distribution is equal to the mean mu and the expected value lambda. This explains why the distribution spreads out as the mean gets larger, as shown in the graphs on the previous slide. The population or process mean mu is the average. The expected value lambda is similar to a sample average. It is based on past data and gives us an estimate of what to expect in the future. If a store had 71 customers in a typical 10-hour day, the mean would be 7.1 customers per hour, and one might expect around 7.1 customers per hour going forward. Key to understanding number 5 says, the binomial distribution converges to the Poisson distribution as its number of trials, n, approaches infinity. One could say that the Poisson distribution is a limiting case of the binomial distribution, or that the binomial is a special case of the Poisson. A binomial distribution has 2 parameters which define it, n, which is the number of trials, and p, which is the probability of a trial. If p remains fixed and n increases, the binomial distribution converges to the Poisson. For large n and small p, say n is greater than 20 and p is less than 5%, one distribution has been used as an approximation for the other. There is a separate video devoted to the binomial distribution. Okay, that concludes our clarification of the concept of Poisson distribution. If you liked this video, please remember to press the thumbs up like button on your screen below. I'll be making more videos of some or most of the 60+ concepts in the book if folks like you tell me that more videos are wanted. Please subscribe to this channel to be notified when new videos are uploaded. Also, the website statisticsfromatoz.com has a listing of available unplanned videos. Now, videos like this one can be very helpful, but they're not very handy when you want to quickly look up something on the job while studying or during an open book exam. For that, nothing beats a book or an ebook. You can also learn more about those on the website. I'd recommend following my blog at statisticsfromatoz.com/blog. I've got some things there that hopefully you will find interesting, like a Statistics Tip of the Week series, as well as posts showing that you are not alone if you're confused by statistics. I'll also be posting on the Facebook page Statistics from A to Z and on Twitter as @StatsA to Z.